Alright, so now we're going to cover a few applications of derivatives. This includes the mean value theorem and Rolle's theorem. So let's just first take a look at an example. Find the equation of the tangent line to the curve y equals 3x squared at the point 2, 12. So before we get started, I just want to let you know that the linear form of an equation is y equals mx plus b, where m is the slope and b is the y-intercept. So the first thing you want to do is find the derivative of the function, right? And in this case, the function is 3x squared. So the derivative of that using the power rule is obviously 6x. The next thing you want to do is plug 2 into the derivative, right? You want to plug the x value of the point that you're given into that derivative. That way we can find the slope at this point. The slope at that point is 12. Then you want to plug the info that you currently have into the linear equation, right? That's y equals mx plus b. So we have our y value, which is 12. We have our x value, which is 2. And we have our m, which is our slope, which is 12. And then we want to solve for b. Using a little bit of math, we can tell that b is negative 12. Then you just plug in your values back into the linear form equation, and you get y equals 12x minus 12. Let's just take a look at one more example. Find the equation of the tangent line to the curve y equals 5x squared plus 3x when x equals 4. So they don't actually give us the y coordinate, but all we have to do is really just plug this in here and we can get the y coordinate. So plugging in the x value gives us a y value of 92. Now then, as previously mentioned, the next thing you want to do is just find the derivative. Using the power rule, the derivative is obviously 10x plus 3. The next step is to just plug in your x coordinate, 4, right? Because you want to find the slope at that point, 43. And then you want to plug the values that you have into the linear equation, which is y equals mx plus b. Now y is 92, right? That's our y coordinate that we got on the first step. And 43 is our slope, and 4 is the point x coordinate. This is the x coordinate of our point. And then we just solve for b. And b in this case is negative 80. So your final answer is y equals 43x minus 80. So in summary, the usual format of the question is find the equation of the line tangent to the function. Then they give you the function at the point hk, right? So the first thing you want to do is find the derivative of this function. Then plug h, which is the x coordinate of the point that you're given, into the derivative that you just found, so you can find the slope at that point. Then using this linear formula right here, you want to plug in your h, k, and m values into the equation and then solve for b. Then you want to rewrite the equation in the format y equals mx plus b with your m value and your b value. Now we're going to cover the mean value theorem. So if f is continuous on AB and differentiable everywhere on AB, then there exists at least one number c on AB such that, so if you take the derivative of f and you plug c in, then that's going to equal the average slope. So that at some point c, the slope is going to equal the average slope. And in case you don't know, these brackets basically mean if the brackets are pointed like this, then that means that you're including these terms right here. And if they're curved, then that means that you're not including them. So inclusive and exclusive. So in layman's terms, there is a point where the slope is equal to the slope of the secant line at the endpoints. So let's take a look at a mathematical example first. F of x equals x cubed on the interval 1 to 3, inclusive. So the first step is just to find the average slope, right? Which is you take the endpoints and you take the x coordinates of the endpoints and you take the y coordinates, so that way you can find the average slope, which is rise over run. That gives you 4. Then you want to take the derivative of the function. Using the power rule, the derivative is 3x squared. You want to set that derivative equal to the